So in this series of videos, we're still looking at how to implement an ordered dictionary. So we have a collection of key element pairs, and we want to be able to insert an item, specify what its key is, but then use that key in order to find or remove an item later. And with an ordered dictionary now, we're also concerned with doing other key-based operations like finding a range of items or finding a a series of elements within a range of keys, or finding the closest key that comes before this one or after this one. So one way that we can do this, what you saw in the previous video, is a lookup table. We're going to see another way that we can accomplish this using a binary search tree. Now this is kind of a basic binary search tree, so you won't see much of an improvement yet when it comes to the efficiency of those operations, but we're going to see a more advanced binary search tree in some of the future videos. So just a basic binary search tree is a binary search tree where we're storing these key element pairs at internal nodes. So again, we're not storing anything at external nodes. This will make some of our cases for implementation a little bit easier later on. But we're very careful to maintain this binary search tree property, which gives an inherent order between elements. So we have always that for a given node, everything in the left subtree is less than that node, and everything in the right subtree is greater than that node. So you might be thinking about how this is kind of similar to a heap in the sense that we define some order, but I want to point out a main difference here, because this is sometimes a source of confusion, that if you go back to using a min heap, what we saw in the priority queue slides, that a min heap maintained this heap order property which said that for a given node, maybe this is 2, just that this root node is less than or equal to all of its children. So let's put it this way, all subtrees are greater than or equal to it. So maybe here we have 5, and here we have 3, for example. So there was no relation between the two children of it. There was only a relation defined between a child and its parent, that a child node is greater than or equal to its parent. Here, we're saying that from this binary search tree property, everything on the left of the root is less than, everything on the right of the root is greater than, which means this left child is less than this right child. And this left child is less than the parent, and this parent is less than the right child, and everything in the right subtree. So this gives a little bit of a stronger order to elements. And because of how this works, that everything on the left is less than, everything on the right is greater than, if we were to traverse these elements in order, and remember, an in-order traversal means we first recur on the left once we have no left children that haven't yet been visited. Then we visit a root node, then we recur on the right. So an in-order traversal would visit 1, and then 2, and then 4, 6, 8, and 9. So this would be an in-order traversal. And any in-order traversal in a binary search tree, because of this property, will always produce an ascending order of elements. So let's see how we would implement those main functions. We want to insert an item, and when we insert an item, we specify what its key is. Also find an element based on its key, and remove an item based on its key. So how would we implement this in a binary search tree? So when we insert, in order to preserve that property that given an item, that entire left subtree is less than it and the entire right subtree is greater than it, we're going to try to find a spot which satisfies those inequalities. So if we want to insert an item with key k, we're essentially going to start at the root node and then determine, does this new item belong on the left subtree or in the right subtree? So if it's larger than this node, we're going to go to the right subtree and kind of repeat this process at that node. And if it's smaller than this item, we're going to go into the left subtree and then repeat this process at that node until we find an external node, which is a free spot that we can insert this item. So our running time for this, I'm going to show an example in a moment, but in the worst case, here's our tree, our huge tree, and this is our root node. In the worst case, we follow a root to leaf path. So this is a path that starts at the root node and goes to the left child, right child, however far down until we reach a leaf node. And that longest path is the height of our tree. So let's see an example of insert. So let's say we insert the following numbers in this order into an initially empty binary search tree. So the first time around we have nothing here, we go to insert 22, and this is the only item we have in our tree. Once we go to insert 80, we'll compare it to 22 because that's the root, and then determine if it's larger or smaller than 22. Since 80 is larger than 22, we're going to go to the right. So we always put those larger elements on the right, smaller elements on the left. Then we go to 18. So we'll again start with the root, compare 18 to 22. It's smaller than 22, so we go to the left, and once we reach this leaf, this external node, then we'll create a new internal node here which stores 18. Now once we go to insert 9, we again always start off with the root and then determine should we go to the left or the right based on how they compare. 9 is smaller than 22, so we go to the left. It's smaller than 18, so we go to the left. And 90. So when we go to insert 90, this is larger than 22, so we go to the right. Now it's larger than 80, so we go to the right again. And finally 20, we compare to our root, which is 22. It's less than 22, so we go to the left. It's larger than 18, so we go to the right. Okay, so this is how we would insert into a binary search tree. Let's see now how we would find in a binary search tree. We can use the same ideas that we did to insert. Start at the root and then check to see first if we found the key we're looking for. Perfect. We can return that entire element and we don't have to do anything else. But if not, then that means it's less than or greater than the key we're looking for, and that will help us determine if we should go to the left subtree or the right subtree. And again, this strategy is based on the height of our tree, because in the worst case, maybe that key doesn't exist in our tree, but in order to determine that, we would start at the root of our tree and follow a path from the root of our subtree to some leaf node in our tree. So the longest possible path that could be is the height of our tree. That's the maximum distance from the root node to any leaf. So let's see an example of that. Let's say this is that tree that we had constructed and we're looking for the number 20. We start at the root, realize that 20 is less than 22, so we'll go to the left. It's larger than 18, so we go to the right until we either find that node, or if we don't find that node, we'll find an external node, a leaf, and we'll know that we should stop there and that it doesn't exist in our tree. All right, now with delete. This is a little bit more complicated than the other operations that we've seen, but the idea is we can certainly find the key that we want to delete just the same way that we would find an element, but we want to remove it without creating any holes in our tree. So an easy case of this is if we have that the node that we're going to remove, n, has at least one child, which is a leaf. And we'll see after that a little bit harder case of if the node we want to remove has both of its children are internal nodes, meaning we can't just remove this because then that would create a hole. So let's see this first. So let's look at the easy case that the node we want to remove has at least one leaf as a child. And in fact, this is an even better case. We have two children that are leaves. So we want to remove the node 9. First, we have to find 9. So we start at 22, realize it's less than 22, and then kind of work our way until we find this node. Then we evaluate what kind of children does it have. In this case, both of 9's children are leaves. So we can take whichever one of those children are leaves and the node that we want to remove, and get rid of this entire thing, kind of scrunch this whole node down to just this other external node here. So once we remove 9, we're getting rid of 9 and its other leaf node. So the only thing that's left was the other child of 9. So you can see now how as long as a node has at least one leaf as a child, we can easily remove it without creating any holes in our tree. So let's say we want to remove 80. Again, how do we know where 80 is? We start at the root, compare, realize 80 is larger than 22, so we move to the right, and then we find that node we want to remove. So in this case, 80 has that its left child is a leaf, so we're going to compress this entire thing, and when we remove it, the new right child of 22, because 80 was a right child of 22, the new right child of 22 will be whatever the other child of 80 was. So the side effect is that entire subtree of 80 kind of moves up by 1. Okay, so that's the first case of removing an item, that the item we want to remove has at least one child, which is a leaf. So let's look at the little bit harder example of if the node we want to remove has both of its children are internal nodes. So let's say we want to remove 18 in this case. So again, we have to find 18, so we start at the root and work our way until we find the node that we want to remove, which is 18. And we identify that both of its children are internal nodes, that they have values stored at them, so we can't just get rid of 18 here, otherwise we would disconnect our tree. So we're going to find the first internal node that would follow from an in-order traversal. So this means we'll go following along an in-order traversal from the node we want to remove. We're going to go first to the right, and then as far left as we possibly can, until this is the last internal node that we would find. So following an in-order traversal, this just means, remember, this is an ascending order of elements, so the next node in an in-order traversal that stores a key will be the next smallest item. So of all of the items in this tree, if we start with 18, the next smallest item, which comes after 18, which is larger than 18, is 19. So this is always just the next node that would come in an in-order traversal. And we're going to take whatever we have stored here at the node we want to remove, we're going to swap it with whatever value we have here in the next the next internal node that comes in an in-order traversal. So we're going to swap the values 18 and 19. So when we have 18 here now, we can guarantee that we're in that position that it has at least one node which is external, because we grabbed that next node that came in an in-order traversal, which means we went to the right and then we went all the way to the left until we couldn't continue anymore. So we know that that left node will be a leaf. So now we can just use the same case that we did before and remove this part of our tree. I want to show one other example here. I'm going to do one more example of this on a larger tree just so you can see how it would work. So let's say we had the following binary search tree. So let's say we want to remove the value 10. Okay, so we've got something pretty large here. We want to remove the element corresponding to key 10. So our first step here is we're going to have to find where 10 is in our tree. So this is our goal, remove 10. So we start at the root, 10 is smaller than 20, so we go to the left and we find, okay, here's that node we want to remove, but unfortunately both of its children are internal nodes. So we're going to find the next node that would come in an in-order traversal, which means we go to the right and then as far to the left as we can until we find the next node which is storing elements. So notice that 11 is just the next smallest item after 10. And we're going to swap whatever's stored at these values. So here we'll now store 11, and here we'll now store 10, which means we are in a good position that now we can finally remove 10 easily because we won't create any holes by doing so. And the new left child of 15 will be whatever the other child of wherever 10 was before, which is here 13. So when we redraw this, this is going to look like this. We've got here 20, 11 is the new left child of 20, the right child didn't change at all. So now we've got 15, and its left child is 13, and the right subtree didn't change at all, but all of 13's children also came up with it. So this is how we would remove 10 from that tree. Okay. So the runtime of remove is also big O of h, where h is the height of our tree. And the reason for that is because we have to find where that element is. And in the worst case, we might traverse the entire, from the root of our tree all the way down to a leaf node of our tree. So the amount of space we use with this implementation is big O of n. This is however many elements we have. All of the operations that we have, find, insert, remove, run in big O of h, where h is the height of our tree. But unfortunately, with just an arbitrary binary search tree, if we have no other additional requirements to this, we just say that we satisfy that it's a binary search tree, which means that for any given node, everything to the left of it in the left subtree is strictly less than that node, everything in the right subtree is strictly greater than that node. If that's the only condition that we enforce, then the height of our tree isn't balanced, in the sense that we could have an unbalanced tree like the following. If we insert the sequence 1, 2, 3, 4, 5 all the way up until n, then every time we insert an item, it's going to go in the rightmost subtree. And then in that case, the height of our tree h would be as large as however many elements we have. Which means that the runtime of all of the operations in a binary search tree is big O of n, because our height is as large as n. So let's compare this to what we've seen before. So with unordered dictionaries, this is, we don't have an order associated with our keys. So we had a hash table was the most efficient implementation. Still, the worst case running time was linear, but we could say that the expected running time was constant. So refer back to the other videos on that. But with an ordered dictionary, we can use a binary search tree in order to implement these functions. Find, insert, and remove element all run in big O of h, but h, our height of our tree, could be as large as n if we don't have a balanced tree, which means we don't really have a better runtime than just using a lookup table. But we'll see in the next videos how we can achieve a balanced tree, meaning that the height of our tree is bounded. In fact, we'll see how we can bound this by log n exactly. And to do so, we'll basically have a binary search tree, but we're going to enforce some other properties in order to make our height be bounded in this way, in which case we'll achieve a better running time for these operations to find, insert, and remove in an ordered dictionary. Okay, if you have any questions, post on Piazza, let me know.